In this video, we'll be talking about the modifications that can happen to a sine function, specifically the graph of the sine function. So what we're going to start with is if I have y equals a, the sine of bx plus c. These values a, b, and c are the values that we're going to have to focus on to understand what the graph is going to look like. Now, if you recall from the previous video, the basic function y equals the sine of x should be built like this. The generic period of the sine function, so the period of the sine function, is normally 2 pi. The value that can modify this is this value right here. B can change the speed at which the trig function is passing through its values. Again, if I plug a 2 in here, think of it as 2 times x, and every time I plug in an x value, that x value is going to be multiplied by that number, forcing it to theoretically move faster. Again, that b value, I'm going to divide the period by the absolute value of that b value. That is going to give me my so-called period. So the generic sine function has a period of 2 pi. I'm going to put that value right here. Anytime I identify the period, that's going to go basically at the last location. Then to find the intermediate values here, there should always be a total of 5 critical points is what we might call them. So I've got 2 pi here. I'm going to cut that in half. Again, that's the pattern which I used for the cosine function in the previous video. That's how I'm doing these. All 6 of these trig functions are going to be built the exact same way. Put my period at the last possible moment, cut in half again, multiply that value by 3 again because I'm counting. It's 1 pi over 2, 2 pi over 2. This would be 3 pi over 2. And then right here is giving me my point for 0. So, one more time, my sine function is going to have a generic period of 2 pi divided by whatever the b value is in this function. So nothing in here, it's not going to move any faster or slower, meaning that the period isn't going to change. The next thing that's important is identifying the max and min value of the function. That's what we call the amplitude. So I'm going to label the amplitude as A. In some cases, I might use AMP for one reason or another. But in this case, the amplitude will always be, well, this value. Because remember, the inside stuff is a horizontal modification of all functions. The outside stuff is a vertical modification. And if you remember, a number on the outside of the function multiplied by the whole function is going to stretch it vertically or shrink it vertically by a specific factor. That's what the amplitude is actually going to do. So in this case, the amplitude value is a 1. So my high point is going to be a 1. My low point is going to be a negative 1. The last piece here, the plus c, we're going to go ahead and talk about that at a later moment, but the important point of it is that's going to be what we call a phase shift. I'm going to label that PS for phase shift. And the phase shift will always be a negative c divided by b. Now, again, it has to be in part that bx plus c, and then this is negative c over b. Now, what's important about that plus c, you'll have to recall, is that an addition or subtraction on the outside of the function is a shift up or down. So the plus c on the inside of a function is a shift left or right. That's what the phase shift is really talking about. And the reason why we call it a phase shift as opposed to a left shift or a right shift is because the function sine is a cyclical function. It continues on forever in that pattern. So all we're doing is we're shifting where that phase, that specific sine curve appears over left or right. And then that b value, again, is going to modify how it's behaving. So the original sine function is 0, high, 0, low, and then back to 0. This is our basic sine function, and it's going to be modified based on these 3 values. Now, what's important to notice here is I've sketched a very small version of the original sine function. Let's go ahead and look at another type of example. What if I had 1/2 the sine of x? What if I wanted to plot that graph? Now, I'm going to use a little bit bigger of a graph here, but what's important here is that this graph is going to tell me everything I need to know. This right here is all I need to graph to be able to clearly identify what this function looks like. So for y equals 1/2 sine of x, on here, I'm going to put a value up here for 1, so 1/2 is going to be about there. Down here, I'm going to put a value of negative 1, and right about there is going to be negative 1/2. That's the only thing that I really need to change in this function. Again, my amplitude then is going to be 1/2. My period is going to be 2 pi divided by b, but there's nothing with that x. Again, b is multiplied by x. There's nothing with that x, so it's simply 2 pi. And then my phase shift, which there isn't any because there's no c value in this function, nothing added inside the sine function. So my phase shift is going to be 0. Okay, which means that I'm going to go ahead and have my last value be 2 pi. That's my period. The last value is 2 pi. I'm going to cut that in half, pi. cut that in half, pi over 2, and then multiply that value by 3 for 3 pi over 2. Don't forget 0 is an anchor point that we need to have, and then we're going to go ahead and graph the sine function. Remembering that the sine function always looks like this curve. So we're going to have 0 for the first point, then my high point, and my high point in this case is based on the amplitude value. My high point is actually 1/2, not 1 anymore. I'm going to go back to 0, then down to my low point, which again is based on the amplitude, so -1/2, and then I'll go back to 0. And this curve looks something like this. Again, making sure that I do my best to show the curvature and not make any really straight lines here. So this is what the sine curve with a 1/2 multiplication on the outside looks like. If I were to graph this function on top of this, superimposed into it, it would look more like this, as I do a dotted line to identify those points. So what you'll notice here is that if I'm going to graph a sine function, I can graph it more or less on the exact same set of axes. The only thing that's going to change is where I put these dashes and what the value at those dashes are. For instance, let's go ahead and do another function, but this time do y equals let's do a -2 sine of x. So for this curve, what is the negative supposed to do in front of the function? Well, the amplitude doesn't change. Keep in mind that the amplitude is still going to be the absolute value of a. So in this case, my amplitude isn't going to be -2, but it's going to be 2, because it's the absolute value of -2 and therefore is 2. What's the negative going to do to the graph? Well, remember, if we look at a negative on the outside of any other function, it's going to reflect it vertically. So it's going to flip the graph upside down. So if I remember these 5 points clearly, what I can do is I can simply say, well, instead of it going up, it's going to go down. So I'm going to go ahead and make that note right here that it's flipped vertically. I'm going to make that note so it's clear to myself when I go to graph this thing that I have to plot those points that way. The period in this case, again, is still unchanged. There's nothing multiplied by the x value, so it's still going to be 2 pi. And my phase shift is still 0 because there's nothing values inside that x. So after I get to here, I'm going to go ahead and plot these values. Now, one more time, it's going to be 2 pi, cut that in half, pi, cut that in half, pi over 2, and then finally multiply that by 3 to get 3 pi over 2. Don't ever forget your 0 anchor point. And then we're going to go ahead and plot the value of 2. Now, notice how I'm going to do this. I'm going to go ahead and draw the xy axis just like all the other ones. I'm not even going to make that 1 value in here. There's no need to do that. I'm going to go ahead and just draw this like where I put the 1 here. I'm going to put the 2 here instead. And then what I'm going to do is I'm going to go ahead and plot the values of the sine. I'm going to know I start at 0 and I'm supposed to go high. But because the graph is flipped vertically, I'm going to go low instead. Again, I'm supposed to go high, but because I'm flipping this graph, it's going to go low, then it's going to go back to 0, then it's supposed to go low, so it's going to go to the high value, then it's going to go back to 0. So then I'm going to go ahead and very carefully curve the function together, making sure that nothing looks like a straighted point location, and it's going to look something like that. That would be my sine equals my y equals -2 sine of x. Notice how, again, it looks more or less just like any other sine curve except for it's flipped upside down, and it's got an amplitude very clearly drawn here as a 2 and a -2. It's got that amplitude value clearly drawn on the axis. Notice if somebody else were to look at this and somebody else were to look at this that weren't taught this information, they would have to recognize that these values are different. That's the only thing that's changed between the image of this graph and the fact that it's flipped upside down. So that's the important part of these graphs. You're more or less drawing the same sine function over and over and over again. The only change that's going to happen is whether or not the graph is going to have different marked values on the axes. So let's do at least one more function. Y equals 3 sine of 2x. So for this function, you'll notice that there's a value multiplied by the x. All that's going to do is it's going to change our period value. Remember that the amplitude is the absolute value of a, the period is 2 pi divided by the b value, so whatever's multiplied with x, and the phase shift is -c over b. So let's go through those values very carefully. My amplitude is going to be 3, that's the value right here. My period is going to be 2 pi divided by the absolute value of b, b being 2, so that means my period is actually just pi. And then my phase shift is supposed to be my -c, but there isn't any c, divided by my b, and that's 2, but 0 divided by 2 is still 0, so there still isn't any phase shift. So all we need to do now is we need to graph the sine function, just like we did all the other sine functions, but this time my amplitude values that I'm going to draw in here for the max and min points are a 3 and a -3 instead of a 1 or a -1. And then I have to figure out how I'm going to graph the function. Well, the pattern that I've been following for all these other graphs is identify the period, put that at the last possible dash, and then cut in half, multiply by 3. Well, this pattern doesn't change. The sine function is still going to behave this exact same way. The only thing that's going to change is the value that we start with. The value that we're going to start with, technically end with, is pi. That's the location of the sine curve for this particular curve where it's going to start repeating itself. Now, if you were to draw this graph like this and just walk away, you would lose all the points for the information at the bare minimum for every single one of these dashes. It has to be clear what we have. So we've got this, this, and this. To find the rest of the points in the middle, remember, cut it in half. That's pi over 2. So pi divided by 2 is pi over 2. Cut this in half. Pi over 2 divided by 2 is actually pi over 4. And then take this value and multiply it by 3. That's just going to give me 3 pi over 4. Don't forget that 0 is always an anchor point. Now, that's a semblance of a lie. The only time that it's not going to be an anchor point is when we have a phase shift that's not 0. Because remember, all these values have to be shifted by a certain amount if there's going to be a phase shift. If the left or right shift, that 0 is no longer going to be a 0. It's going to be something else. So once I have these 1, 2, 3, 4, 5 points or dashes identified, then all I have to do is fill in the values for sine. Remembering that sine is 0, high, 0, low, 0. And if I draw this nice smooth curve, this is going to look like every other sine function as I have already drawn, other than the one that's flipped. Except for the only difference between, again, these curves and this one down here is the fact that I know that the actual axes labels matter. Whereas in other graphs, you might just go ahead and dash 1, 2, 3, 4, and so on and so forth, as well as -1, -2, -3, and so on and so forth. We are actually labeling only the points that are going to matter in this graph. We do remember, again, that this graph continues on forever in both directions. If that's the case, and it doesn't ask us to graph only one period of the function, then we have to continue graphing more values. But if this just says graph one period of the function, these are the 5 anchor points I'm looking for. I got to make sure I label the max and min values, the amplitude values, and then I have to make sure I draw the nice smooth curve, identifying those main 5 points. Again, making sure that you plot those actual points. We're going to go ahead and cover the phase shift examples in another video, but this is the concept of how you start every basic trig function, be it sine or cosine, secant, cosecant, tangent, or cotangent. The difference is that sine and cosine behave with this pattern. Secant and cosecant also behave in this pattern, but tangent and cotangent don't agree with these values. That's going to be, again, another change, slight change to how we graph all of the 6 trig functions.